Okay, a wind is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. Oh, I forgot something we were going to do first. We're going to do this one problem, and then we're going to go to Canvas real quick and do something. 30 degrees south of west. Find the westward and southward components of the wind. Okay, so we're going to draw a vector for this wind, and then we have to break it down into the westward and southward components. So anytime you have one that involves north, south, east, west, you want to start off with your north, south, west over here, east over here. Make sure you know your directions well. So wind is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. So south of west tells me that west is my main direction, and I'm going 30 degrees to the south of that. So when I draw this vector here, I will have a dot on this end. That's where I'm starting. And I will have an arrow on this end, and this angle right here will be 30 degrees. And I will label the length of this side as 45. Okay, so something we're going to do here in a minute is I've got an angle direction assignment that we're going to look at real quick before we go any further after we do this problem, because being able to answer this question, like being able to know which direction the wind is blowing, is going to be a big part of this, knowing whether it's south of west or west of south. In fact, there's two ways you can answer those. For example, this angle right here can be 30 degrees south of west. That's probably the most standard way to talk about it. But there's another way you could talk about this same vector. Okay? What would the angle on this side be? It'd be 60, right? So you could also call this 60 degrees west of south. You could switch them. So there's two options for every angle that you're given there. But this particular problem asks us to break this down into a westward and southward components. This is a little bit different than the ones you looked at on the notes, because this is giving you your answer vector. Okay, this is the answer. We have a westward component and a southward component. We're putting those together, and this is the answer. So if we make a parallelogram here, where this part right here is our answer, we would have a westward component, which I'm going to do in green here. I'm going to call it W. And then we would also have a southward component. So this one gave us the answer, and we're having to work backwards to break it apart. So what we're going to do for this is we're going to look, and we're going to look at a triangle. I would probably pick this triangle here, because we know the angle that's in that triangle. And we're going to be able to find the two sides of that triangle, okay? Because I know that the hypotenuse here is 45. I also know that south and west are perpendicular to each other, so that's going to be a right angle. Right there, we're going to have a rectangle. And I also know that this side over here would be S, because we're dealing with the rectangle here. So we can find S or W first. It does not matter which one that we look for. First, what do you think, Connor? Which one do you want to find first? Okay, so if we're looking for S, all right, in this triangle, S, well, you got two up. Let's try to do regular trig. On the quiz that you guys took, a lot of you guys are using law of sines to do everything, which is okay. It will make I think it will be good if we use regular trig for this. Law of sines will work, but I think it will be good if we use regular trig here. So keep in mind that sine of your angle is opposite over hypotenuse. Cosine of your angle is adjacent over hypotenuse. And tangent of your angle is opposite over adjacent. So if we were looking at this highlighted triangle here, our angle is 30 degrees. And if we are looking for S, would S be opposite, adjacent, or hypotenuse here? It is opposite. 45, is that opposite, adjacent, or hypotenuse? Hypotenuse. And we're going to have to find W eventually, opposite, adjacent, or hypotenuse. Adjacent, right? Okay, so to set this up, if we're looking for S, S is opposite, and we know 45 is a hypotenuse. So we would say sine of 30 degrees equals S over 45. Which is just going to be a one-step solve here. We just got to multiply by 45 on both sides. And let me get the other calculator. I'm going to put that one in degree. Make sure your calculator's in degree for this. 45 sine 30 is going to give us 22.5. So S is going to be 22.5, and this would be miles per hour. That is your southward component. Is everybody okay there? Okay. You're going to do basically the same thing for W, but what should we use for W? Well, you can use tangent because we have found the opposite side. So you can use tangent. Actually, there's several things you can do here. You could use tangent or cosine, or there's a third thing you could do. This is a right triangle. We already have two sides. You could do law of sines. Okay, fourth thing you can do. You could just do Pythagorean theorem for this. A squared plus B squared equals C squared. I think cosine is the easiest thing to do because you don't have to worry about any like rounded values or anything. This one was nice. It was like 22.5, but sometimes it's a big long rounded. You have to round it off. So I would use cosine. So cosine of 30 degrees would be adjacent over hypotenuse, so W over 45. And we would just have to multiply both sides by 45 here as well. And for W, we will get 45 cosine 30 is going to give us 38.971 miles per hour. That would be your westward component. Okay, questions? All right, we're going to stop with these notes for a second because with our notes here. Just like the application problems for our law of sines and cosines, the picture is so important on these. Getting the picture right is one of the main things you have to do. So a sled is being pulled with a string. The string makes a 62-degree angle with the ground. The person pulling the sled is exerting a force of 4 newtons. What are the horizontal and vertical components of the force? So if you were analyzing this situation, it would be very important for you to know this. Particularly, I have just done a sled being pulled by a string because I felt like that was probably something everybody could picture and was pretty familiar with. Probably when you're pulling a sled across flat ground, you're not thinking too hard about forces and angles and vectors, right? But you could take this and apply it to something different that would be probably more technical. For example, if you had like an assembly line and there is a rope pulling something, you can think about the force that it's going to have on something within a machine or something that would be much more complicated but apply the same principle. But I tried to stick with things that would kind of make sense for what we know. So it does not say flat ground, but it should say flat ground. Because if the ground is not flat, that does change the problem quite a bit. And it's very likely you might be pulling a sled up a hill, in which case the problem gets more complicated. But this one is going to be a flat ground problem. So we've got a sled over here. So here is our sled. We didn't need it this year at all. Not even a little bit. And over here we have our person. And they are pulling. Actually, let me draw. Well, they're pulling the sled, and it's making a 62-degree angle with the ground. I've drawn my sled where it's sticking up off of the ground a whole lot, which could actually affect this, but pretend it's all the way to the ground, you know, there. So this would be broken down into a horizontal component and a vertical component. Now here's why this is important in this particular case. I need to just draw my, hold on. I need to draw my sled a little. It's going to look better if we do it like this. They tied the rope to the bottom runner right here, which is a terrible idea. This rope's going to break, but we need it to look better for our picture, so let's do it that way. If you're really wanting to analyze this closely, I guess you should consider how high the rope is off the ground, but we're not going to do that. Alright, so there's a good reason why this would be important here. As you pull this sled along the ground, the only force that's actually doing any good is your horizontal force, right? Because you're just wanting to pull that rope, the sled across the ground. You have no intentions of pulling the sled up, right? So the most efficient way possible to pull this sled would be to only pull it with a horizontal force. But why would you not do that? You'd have to be on the ground to do it, right? I guess you maybe, what if, we should try this out. You should do it like, we should try, this is actually a good idea. We need, like, you know how boogie boards have those, like, things where you put them on your ankle or your wrist so you don't lose them in the ocean? We could put one of those on our sled and strap it to our ankle. More efficient pulling of the sled. That could cause a problem. Yeah, could cause a problem. This will only work in already packed down snow, or if you're wearing snowshoes. Yes. But and if we don't want to have some sort of apparatus where we can pull this straight down, we're going to have to get on the ground and crawl to pull it. So while it would be more efficient in the pulling of the sled, it's much less efficient for the human body to have to crawl on the ground, right? So nobody really wants to do that. But any upward force is basically just wasted force because you're not pulling the sled anywhere with that upward force. For example, this particular stick figure has decided that this is the best way to hold his arms as he pulls the sled across the ground. So he maybe could adjust his form a little bit to get more efficient use of the force here. But we can analyze how much of that force is actually being used to do the work and how much of it is just kind of wasted for convenience, right? So we've got this force right here is 4 newtons. We want to break that down into horizontal and vertical force. I'm going to call this right here X. I'm going to call this Y. We know vertical and horizontal are going to make a right angle right here. So if I want to know the horizontal force, then we got to think about opposite, adjacent, hypotenuse. 62 is my angle over here. This would be opposite. This would be adjacent. The 4 right here would be my hypotenuse. So for horizontal, I would have adjacent, and I know hypotenuse is 4, so I would do cosine. So I would do cosine of 62 degrees is X over 4. And that's a pretty simple solve. Just multiply both sides by 4. Might have closed my calculator out. And if we do 4 cosine of 62, we are going to get 1.879 or 878. So X is 1.878 newtons, and this is horizontal. Okay, let's see. Liam, what if I want to find the vertical force? How do I find it? What? Sine? Yes. So sine of 62, what would it be equal to, Liam? Perfect. We will multiply both sides by 4. So for sine 62, it's going to give us 3.532. And that's our vertical force. Getting the pictures right is so important. So I personally prefer the triangle method. I think that video showed you triangle and parallelogram, but I have found kids cannot do the triangle method right. Most kids. If you like triangle method and you get it figured out on your own, go ahead and use it. I don't mind. But I have had much better success in teaching this since I started teaching kids to do the parallelogram method. So in general, what you want to do with parallelogram method is you're going to put both vectors with the same endpoint. And then you will make a parallelogram, which for this particular case is going to just be a rectangle, like so. And your answer vector, your resultant vector, is always going to be from that common endpoint to the opposite corner. And please, when you draw these, please, please, please put endpoints and arrows on your drawings. Because what I find students do a lot of times if they don't do that is they'll draw in their vector like right here, which would be wrong. It's not going, your direction is going to be way off. Your magnitude will still be okay, but your direction will be way off if you do that. So you need to go common endpoint to opposite corner. Make sure you put endpoints and arrows there when you draw them. Okay. If you're doing one like number 2, you would make a parallelogram. I just always do that by drawing parallel lines as best you can. It's hard to do it perfectly. Okay. And your resultant vector is going to go from that common endpoint to the opposite corner, like that. Okay, does that make sense? All right, so let's do one of these others together. So you're going to do 3 and 4. Let's do 6 together, just to make sure we're on the right track, and I'm going to let you do a few of these on your own. So a wind blowing has a northward component of 30 miles per hour and a westward component of 15 miles per hour. In what direction is the wind blowing? So northward component of 30, westward of 15. So I'm going to draw my north, south, east, west, but north and west is where I need the most room, right? I have a northward component of 30. So I'm going to start at the origin here. I'm going to draw myself a vector, and I'm going to label it 30 miles per hour. I also have a westward component of 15. Try to draw these a little bit to scale. Tomorrow we're going to do some like difficult problems, and I'm going to get out the rulers and protractors, and we're going to actually draw them perfectly to scale, because sometimes if it's not drawn to scale, it makes it hard to answer the questions. On the ones with the right triangles, like we're going to see today, or pretty straightforward parallelograms, as long as you're close, it's going to be all right. It doesn't have to be perfectly drawn to scale, but try to get it sort of close. So I'm going to draw this it's going to be shorter. It's going to be 15 miles per hour. And also just use some sense here. If I have a westward and a northward component, then the wind is going to be going between these somewhere, right? So whenever you draw this, you're going to do a parallelogram, which is just a rectangle for this problem. And your resultant vector is going to go from the endpoint to the opposite corner. Okay, you do not want to draw the vector right here. You'll get the same magnitude, the same speed, but you'll get the wrong, I don't even know how to say what direction that is because it doesn't intersect at the origin here. So don't draw it that way. So this particular problem, does it even ask for the magnitude? What does it ask for? Direction. So it's only asking for direction. So I do not have to find the magnitude. If I wanted to, it would be very simple to do, because if this side is 15 and this side right here is 30, that means this is 30, this is 15. We would know these would both be right triangles. You've got two sides. It's just a squared plus b squared equals c squared, because that's a right angle. So that would just give you the speed if you needed to find it, but it didn't ask us for that for this problem. It asked us for the angle, or the direction. So we have two options on finding this angle. We can either use this bottom angle right here or the top angle right here. It needs to be one of these two angles next to the origin, not the angles over here in the triangle. I'm going to pick this one, the top one, but you could just as easily pick the bottom one. There's no real reason why this would be easier. So if I'm looking at this triangle right here, then this side right here would be opposite, and this would be adjacent. And whenever I have opposite and adjacent, what trig function do I use? Tangent. So I would say tangent of my angle, which I don't know what it is. I'm going to call it theta right now, equals 15 over 30. How do I solve that? How do I get rid of tangent? What is it? Inverse tangent. Alright, so I will do inverse tangent of 1/2, 15 over 30, same thing, 26.565. And what is that? Is it west of north or north of west here? West of north. Now, if you're doing this problem, because whenever we get to the test, these are going to be multiple choice. I might have type in box answers if I ask you for the magnitude, for the speed on this. But if I'm asking you for direction, it's going to be multiple choice because that's hard to type in and type it in correctly for Canvas to grade. So it's going to be multiple choice. What if our answer's not there? We can do 90 minus that number, and we'll get 63.435. And that would be north of west. So either of those are correct. You just need to look and see which one's available for the answer choice. You don't have to give me both for anything, but because it's going to be multiple choice, and there's really not like anything telling you that you should use this angle instead of this angle here. Either one is equally easy to set up. Looking at these, right here, you know, this is 0 degrees, and then this would be 90 degrees, and this would be 180 degrees. This would be 270, and then if you go back around, it'd be 360, and then you could keep on going more than one rotation, but you won't see that on these problems. So 80 degrees is going to be sort of like in the west direction, although don't use north, south, east, west because it didn't have that in the problem. And then 27 is going to be in the sort of south direction there. So you'll draw your parallelogram. Your resultant vector, the answer vector, is the one that goes here. So whenever we're given angles like it gives in this problem, just like straight angles, it doesn't say north, south, east, or west, you are always finding the angle from 0 degrees around to that angle. So in this case, you can't really find that whole angle right away, but we could find this angle right here, and then we could add 180 to it. So you're going to set that up. Tangent is going to be 27 over 54. You'll do inverse tangent, which is going to give you 26.565 for this angle. You will add 180 to it to give you that direction that is just like a general direction on the coordinate plane. If you remember doing a little bit of unit circle stuff back before, that's how the angles work on that unit circle. You just always start at 0 and go in the counterclockwise direction that far for that angle. And then the magnitude is just Pythagorean theorem. Okay. 6, you are either going to get 26.565 degrees west of north or 63.435 degrees north of west. You don't have to have both, just as long as you got one of them and your directions are correct. For 7, you should either get 60.6 255 degrees south of east or 29.745 degrees east of south. 8, you should get 33.690 degrees north of east or 56.310 degrees east of north. Again, there's not really like a better answer for those. It just is whichever one you happen to get. For number 9, I found this angle right here. So, and really to be like a little more specific, I could say 75 degrees, 0.069 degrees to the horizontal. Okay. You may have found this angle here. If you did, you found the angle to the vertical, which is fine. There you would just say it's to the vertical. On a quiz or test, it's either going to be a little more specific and say, find the angle that the object will make to the horizontal, or the answer choices might say to the horizontal on it, or to the vertical for that. And then let's go ahead and do 10. Several of you had done 10. 10 was 32.139 degrees is your, I'm sorry, not degrees, 32.139 miles per hour is your southward component, and 38.302 miles per hour is your eastward component. Okay, I know you may not have all had time to get to all of those yet, but this is posted on Canvas so you can see it. Okay, let's do a few that are not right angles. Okay, vector A has a magnitude of 3 centimeters and a direction of 0. Vector B has a magnitude of 4 centimeters and a direction of 50 degrees. So for this problem, let's turn my recorder back on. Oh wait, no, it's been recording the whole time. I'm going to have to edit that out. All right, so if we have the origin here, our first vector has a direction of 0 degrees and a magnitude of 3 centimeters. Our second vector has a direction of 50 degrees and a magnitude of 4 centimeters. So it's going to be a little bit longer. And this angle right here is going to be 50 degrees. So this is not going to create a right triangle because we are going to have to make a parallelogram. So we do that by making lines parallel to the vectors that we have. And our resultant vector is going to go from here across to the other side. Now, here's the problem. I've got 2 triangles. Do I have any of the angles of those triangles? I don't, because 50 got split in half, but it's like we don't know for sure that it's half, right? The only way we would know it was for sure half is if this was 3 centimeters and this was also 3 centimeters. Then it would be split in half. But it's not really split in half, so I don't know how much of the 50 is up here and how much of the 50 is down here. So I'm going to do this. I'm going to take away my vector I just drew, just so you guys can picture it a little bit. I have a parallelogram. If this is 50 degrees, what is the angle over here? Also 50 degrees. All right. What do the angles of a parallelogram have to add up to? Not 180, that'd be a triangle. 360. Okay. So that means that I've got 50 here, 50 here. So 360 minus the 50 minus the 50 is going to give me 260. And that has to be split between these 2 angles here. So what are these angles going to be? 130. Okay, now I'm going to draw my resultant vector back in. There's no reason you can't have the resultant there while you're doing that. I just think it's a little easier to picture without it there. So now, if I look at this angle this triangle right here, now I have an angle, and I've got two of the sides. Because I know if this side right here is 4, this side right here would also be 4. So I've got two sides and the angle in between. This is not a right triangle. I cannot do regular trig on this. If I have two sides and the angle in between, what do I have to use? Cosines. So I would say, I'm going to look for this side right here first. X squared would equal 3 squared plus 4 squared minus 2 times 3 times 4 cosine of 130. And so that will give us this number. We need to take the square root of that number, and we'll get 6.358. Hello? Yes, thank you. Gabby, at the end of this class, when the bell rings, you need to go sign out. Okay. All right, so that is the length of this side. Now let's think about what we've got. Sometimes I like to pull this off of the bigger picture because it gets a little complicated. This was 130. This was 3. This was 4. We just found this side right here is 6.358. We want the direction. The direction needs to be this angle right here. It needs to be the angle between 0 and our resultant vector, right? So we're looking for this angle right here. And we can use law of sines for this. So we would have sine of 130 over 6.358 equals sine of theta over 4. Okay, so we're just doing that side across. And so we cross multiply 6.358 sine theta will equal 4 sine 130. We need to divide by 6.358. So, to be most precise, we could do 4 sine 130 divided by, I'm going to click that answer button. If you round it, you might be a little bit off from what I'm getting. And then if you do sine inverse, well, let me write that part down. So guys, sine theta is going to equal 0.4819. If we do sine inverse of that, we will get I did sine. I did not do sine inverse. That seemed, it's possible that the angle could be 0.008 degrees, but it seems unlikely that that would happen right there, right? I did sine instead of sine inverse. So sine inverse of, I'm going to type it in, 48192. Oh, that's going to mess it up bad too. 819241873. Okay, let's try that. Okay, that looks more reasonable, right? So we're getting theta is 28 degrees. I've kept 4 decimal places. That's fine. So our magnitude is 6.358 centimeters, and our direction is this 28.8111 degrees. Okay, questions? All right. Let's do one that's actually like in context now. And this will probably be the last one we have time for. So an airplane is flying due west at a velocity of 120 meters per second. The wind is blowing 20 degrees north of west at 15 meters per second. What is the magnitude and direction of the plane's resultant velocity? So we've got west and north. So I need north, south, east, west, but mostly north and west here. And the plane is flying due west at a velocity of 120 meters per second. The wind is 15 meters per second, and it's 20 degrees north of west. So it's not going to be very long in comparison. In fact, I probably drew it a little too long there, but it'll be good enough. 15 meters per second here. This angle would be 20 degrees. We would have to make a parallelogram. Okay. Before we do our resultant vector, which will go from here to here, let's think about this parallelogram. An even shorter way than the way I did it last time. In a parallelogram, the two angles right here, what we call, what do we call those? Adjacent angles, I think. Ones that are on the same side, they have to add up to 180. So if this is 20, this will be 160 right here. So our resultant vector is going to go like this. We need the magnitude and direction. You have to find magnitude to find direction on these problems anyway, because you can't find direction yet. So we could find this side right here. Again, sometimes you may just want to like pull it off, make a clean drawing. This side is X, this side is 120, this side is 15, this angle is 160. So we could do X squared equals 15 squared plus 120 squared minus 2 times 15 times 120. I know I'm moving a little fast. We're about out of time. Cosine of 160. And so if we type that in, 15 squared plus cosine 160 is going to give us this number. We are going to square root that number. We're going to get 134.193. So 134.193, that is our speed in meters per second. So the magnitude is the speed on that. And then the easiest angle to find here is going to be this angle because it actually touches the west direction. Okay? You could find this angle, but then you're going to have to subtract it from stuff to find either the angle here or angle here. So you would have to do sine of 160 over this number, 134.193, equals sine of theta over 15. And so that would give us 15 sine 160 equals 134.193 sine theta. We'll divide we'll get 15 sine 160 divided by the answer from the line before. That gives us this. We have to do sine inverse. And we'll get 2.190 or 2.191 degrees, and that will be north of west. Okay. For that worksheet, finish that up for me tonight. We will look at it. At least try something on problems, especially when you get to these harder ones. If all you can do is draw the picture, that's going to get you credit for your homework, okay? So at least try to draw something for each one. We'll spend some time looking at these tomorrow as well.